What's poppin'? It's Buzo Builds with another tech banger. So for this project I decided to build an Arduino powered game console with an LED matrix display and a really crappy controller since the wires are sticking up everywhere. Anyways, I built this project without any libraries whatsoever besides the standard Arduino and C++ libraries. This means that yes, I programmed my own LED matrix library and game library because who doesn't love to torture themselves? The way the game console works is that you upload a game sketch that makes use of the LED matrix and the game libraries that I made, and then a game comes on and you use the really awkward controller to play the game. So currently I'm a bit embarrassed about the code quality of the libraries to post it on GitHub or something. I rarely code in C++, but if enough people ask in the comments, then I'll fix it up and post it. As you might notice, I was able to destroy enemies in the game, but when enemies touch me, I don't die. Why is this? Am I simply just a god? Well, nah. I didn't implement the dying feature within the games because the controller is really crappy. So if I actually have to play the game with the risk of dying, then I would have not made it too far in the game, and I would not get any good footage of the project, and then my channel would be trash, and then my wife and children would leave me. So well, with all of that said, let us get into the video of how I built this. Cue intro. So, I had an idea of how to make video games. In fact, video games were the first programs that I wrote. I also had an idea of how to use an Arduino. I've been using Arduino for some time now, although I learn new things every time I use one. What I had no idea about though was how to freaking interface with an LED matrix without using a fancy library. I originally thought that there would be a pin for each LED that made up the length and width of the board, so to turn on an LED matrix, you would just send the signal to the 2 points whose lines would intersect at the point where the LED was, but turns out that that was only true for small LED matrices like an 8x8. For larger LED matrices, which this project required, it was a whole different story. So, being the loser I am, I decided to do some research on how large LED matrices operated. So, my first objective was to find a data sheet for an LED matrix, because that is what any sane person would do, right? But of course, the internet decided to flip me off and there was no data sheet. So I was like, fine, let me just scour the web until I understand how these devices work. Luckily, I found some really amazing websites, authored by really amazing people, that broke down how the large LED matrices work and how to interface with them. So how they work is that the rows of the matrices are partitioned into sets of two non-adjacent rows, which I'll call row pairs. Each row pair is addressable using the address pins. There are 4 address pins on a 32x64 matrix, meaning that we can address 2 to the 4 or 16 row pairs, or which means 32 rows, which are exactly how many rows there are in the matrix. Only 2 rows can have LEDs on at the same time. The matrix operated like a serial in parallel out shift register, in the sense that in order to actually input data to make the lights go on, we would need to, for each column of the addressed row pair, serially input 6 bits at a time, red, green, blue, binary data for both the LEDs in the 2 rows, trigger the clock pin, and then enter in the next set of 6 bits for the next column. After entering in the 6 bits 32 times, you need to trigger the latch pin to store the data and make the matrix to output the data in the form of turning the LEDs on. After this, you will need to address a new row pair, probably increment it, and clock in the bits again, and you keep doing this forever until you die. This was more of a summary of how matrices work. For more information, check out the description for websites on the matter. So, after getting a better understanding of how the matrices work, I wanted to hook up an LED matrix to the Arduino to test/validate my research and to answer some questions that I had, such as which clock pulse corresponds to which column when clocking in the data. Okay, and now it's time for the moment of truth. We wired up our LED matrix, we got our Arduino, About to upload this code. Hopefully the code is written correctly, and we'll see if a pixel shows up on the LED matrix. Or is this thing just gonna catch on fire or something? Let's see. Oops, I'm using the wrong mouse. Says upload done. I don't see a pixel on the screen. So I don't know what the bleep 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 is going on. LED lights are coming on, that's cool. But there's like some unexpected behavior with both turning it on and turning it on and like clearing the screen. Let me just show you. So right now I have code to clear the screen. Clears the screen, but it does some weird stuff. It's like it moves the lights up and all that jazz. I'm just like, huh, what's going on? So I had 3 goals for LED matrix testing. I mean, to make any pixel whatsoever light up. 2, make the first pixel of the first row pair light up. And 3, fill in the row pairs with a specific color and make the last 2 pixels of the row pair another specific color. The first goal was pretty easy, kind of. You guys just saw me fail on the goal, but I surprisingly got a red pixel on the LED matrix in a short amount of time. But that success came with an issue. I had to run the program twice to get 1 LED on, 3 times to get 2 LEDs on, and so on. For some reason, the LED matrix was always 1 LED behind. This behavior kind of went against my second goal because the position of what LED was to be turned on was based on the clock cycle and the address line. So I spent hours digging online and meticulously picking apart my code, trying to find the reason for what this somewhat strange behavior and after a lot of debugging, it appeared to be the case that I needed to pulse the output enable matrix pin in order to show the new output that the latch contained. It also turned out that I was accidentally pulsing it at the beginning of the code due to the fact that some of the Arduino pins were emitting a high voltage despite not even being set on. Output no high. Regardless, I invented these facts into the code, and now I have control over which, well, I'm speaking in the current tense, and then I ended up having control over which LED I can turn on at any time. This allowed me to easily accomplish goals 2 and 3 in regards to the output enabled situation though. I don't think all boards work the way I just described. Instead, they output exactly what's on the latch, but for some reason my board just required that I push the output enable pin, pulse the output enable pin. Man, figuring that out was such a headache, but I'm happy to have properly debugged the situation. Now that I had a more concrete understanding of how LED matrices work due to our painful and soul-crippling experiments, I can now confidently code functionality for the matrix. So this was just a little animation that I was able to do when I got the matrix library working and stuff. You got this blue line just lining it up over there, and you have the square from the left and right one. So yeah, I thought that was pretty cool. Boy, I tell you, I ran into many issues when implementing the LED matrix graphic library, but I'll just talk about 3 major issues I had. The first issue was that despite being able to determine the position of a pixel when the address lines were static, when attempting to create a loop that touched each address so that I could draw on the whole matrix, besides on just 2 rows, the image that I would produce would become 1 address off. For example, when I tried to put a pixel at row 0, it would be at row 1, and if I tried to put a pixel at row 3, it would be at row 16. Turns out that the way I was performing the loop to address all the rows had a timing issue, making the output only show briefly for the right row and then permanently show for the wrong row. After identifying this timing issue, I tweaked the cycle within the loop and it freaking worked. I got a white pixel on the bottom of the left corner on the LED matrix, baby. Woo! The second and third issue I ran into dealt with memory, or Arduino's lack of it, which is pretty cool to be honest, because unlike them boomers, I never really dealt with memory issues in my programs. So it was interesting experiments. And I tell you, when Arduino runs out of memory, hide your kids, because the Arduino just goes ape crazy. But anyways, I had to make a bitmap to represent the pixels and their colors. I originally thought that a boolean was a bit, so I thought the most efficient thing to do was to make a 32 by 64 by 3 boolean matrix to represent the pixels, where the 3 booleans represented different possible colors, RGB being on or off. Turns out a boolean was a whole byte, and the Arduino only has about 8,000 bytes of memory. So the bitmap alone was consuming 64 times 32 times 3 bytes, which equals 6,144 whole bytes. That's about 77% of Arduino's memory dedicated to only bitmap, not even the actual game. Luckily, the internet enlightened me about a boolean's true size, and I decided to use a 64 by 32 character matrix instead. Yes, it's still efficient, it's still inefficient, because each pixel only needs 8 different values, 3 bits, but to my knowledge, a character was the best that I can do. Anyways, this change results in the bitmap taking 64 by 32 bytes, which equals 2048 bytes, or about 26% of Arduino's memory, which is much more workable. I'm a bit embarrassed to talk about the third issue because it reveals my trashy engineering skills. But when thinking about how to implement the graphics library, I wanted to focus on animation and such because that's what happens in games, animation. So I decided to make this complicated tree data structure called an image, which essentially holds all of the pixels of an object. I did this nonsense move because I decided that if I wanted to translate the object, I could just increment the position of all the pixels in the object. But the big bad lack of memory problem came back, and thank God it did, because that implementation was trash. So after finishing the graphics library with this horrible implementation of mine, I decided to go take a walk, feeling like that guy. Then, I don't know what happened, but the stars and planets converged, sunlight seeped through the clouds, and I was enlightened. I decided that I did not need to actually keep every pixel in memory, just keep track of one pixel's position, and then draw the other pixels relative to that pixel during translation. Literally like how any other sane person would do it, not this image tree monkey hoo-ha baloney. Now that I finished making the graphics library for the LED, which can draw pixels, squares, and lines anywhere on the matrix, it was time to code up the game library to help me write the games that I'll be writing for our new game console. The game library would be built on top of the services of the LED matrix library because it would use the library's functions to display its game contents on the LED screen. The main components of the game library were the frame rate controller, which managed the frame rate of the game object class, which was the base class for every interactable object in the game, and the controller, which was basically their software representation of the controller that I built. Coding the frame rate controller and the game object class was relatively easy because it was pure software. Sure, the game object had to somehow draw its contents on the screen, but the LED matrix library that I already made took care of that. All I had to do at this point was call a drawing function and the library abstracted out all of the messy hardware. The controller portion of the library, though, was a freaking ding-dong because it was interfaced directly with the controller hardware. When testing out the buttons for my controller, I actually short-circuited my Arduino. I didn't know about pull-down resistors until after. I think the short-circuiting is what led to half of my first LED matrix screen to stop responding actually. Thus, I had to order more LED matrices. So, the way my controller worked before was that anytime a button was pressed, an interrupt would be generated on the designated interrupt wire/pin. When the Arduino detects the interrupt, it will determine what specific button was pressed and register the button input into a queue. If the input was processed and the button was released, then the input would be dequeued. The system was meant to prevent the game console from missing any input strokes and enabling button holding. So logically, this made sense. But that darn thing called time was like, nah, you're not going to implement this fancy dancy controller input system without a fight. So after hours of debugging both hardware, not my specialty, and software issues, and dealing with things such as bounce, circuits, disconnecting, and other bull manure, and also learning that a polling based system is actually recommended for user input, I ended up implementing a more simpler hybrid polling interrupt controller system, which performed decent, although there are still some hiccups with the controller that I may or may not fix later. So, that was my journey of how I built an Arduino powered game console without any special libraries, unless you mean your local library. But future work on this project would probably involve fixing some bugs, such as the double line bug, where on two specific rows, the LED matrix shows the contents of the rows on their row pair counterparts. I think this bug has something to do with my display loop or something, but the bug isn't big enough for me to try, and I'm kind of tired of this project now. Another bug slash future work is to make the controller input more responsive, and finally it would be cool to add some sound effects and 8-bit music to the console. Anyways, that's all for now, folks. Happy coding!